Okay, today I want to put together a quick video talking about state machines and stack machines from a sort of abstract perspective and clarifying some things about them. So I'm going to probably just use Scratch for this and talk about ideas. Don't have a plan to switch to the code, so I probably won't. Okay, so first of all, topics, state machines, stack machines. And within this, I'm going to want to make sure I remember to hit a few things. So I had someone ask, and I want to make sure to cover, just to clarify about the idea that you have a next and push logic. Like there's an operator where you do a next and push. And so I'm going to talk about that. And then I want to provide like the basic definition of a state machine and the basic definition of a stack machine. Well, we'll arrive at the stack machine by sort of modifications to state machine. And so I guess the stages, let me just write down the stages of modification. So first you add the stack, and I think maybe I should just figure it out from there when I'm going through it. Maybe there's like these steps, like you add the stack and then you look at an example where you want to be able to do something with the stack and then it doesn't quite work what you want. We'll also talk about the metaphor build from state machine. There's the metaphor to lines of code. Slash instructions. I think that's a good outline for us to go with. Okay, so state machines. The basic idea here is that you have a state machine has a set of states. So I'm going to write that like this. So this is a notation I want to use where n, if n is, let's add this to the top, some notation stuff. So let's just go over some notation stuff I want to use. If n is an unsigned integer, so any unsigned integer. Oh, one sec. Okay, continuing. So if n is a uint, is what I'm going to write, an unsigned integer, then this notation here means the set, and then let's make it the zero indexed set of integers that contains n elements, right? So it doesn't actually contain n, but it contains all the unsigned integers less than n, which make up the index set to an array that has n elements, right? Okay, so that's what the square brackets n sort of means for today. And so a state machine is essentially a way where you go, we've got some, n, we'll call this like, maybe it's, s is our finites, is our states. And the trick here is you go, so like maybe we can say like this, you have states is some kind of finite type. So there's this idea that like, we're going to just start building stuff out of saying we have finite types. What this really means is that there's just some count. It's one of these things, right? So my notation for this stuff changes all the time, but let's say this, okay? It's a finite set. And so you have some set of states, and you also have another kind of finite set here, which is like your input type. And then what happens is that a state machine gives you a specific arrow. In an arrow in the sense that it maps information. So if you have an array of inputs, a state machine gives you one of its states. Let's say a state looks like this, right? So if you have an array of inputs, it gives you a state essentially. And then we can talk about what's the way that it does this. And essentially the idea is a state machine is the sort of thing where you have a state and an input come together into a pair, and you pick a new state, right? So your input now is like, it's an array of inputs. This can be an array of characters, an array of bytes, array of bits, whatever. It can also be like key presses, though, right? This could be an array of key presses. Or you can reinterpret this however you want. That's a part of the idea of saying it's a finite set. The definition now works whatever finite set you find in your programming systems. Anytime you've got an enum, anytime you've got just a collection of things, a symbol set, whatever finite sets you have can just become the thing that implements any of these things that I called a finite set, state or input, right? And so then the idea of a state machine is that it's got some kind of state, and you are going to you get an input array, and you're going to calculate a state. And so the way, like the kernel of it, though, it's built out of this kernel where you take a state and an input together and map that to a new state. And this is really the kernel of it, right? If you take this information and then you pick an initial state, right? So you say like we have our step function and we have an initial state, right? This information actually defines the inside of a state machine, right? So a state machine has this mapping from a state and an input to a state, and it has an initial state. And that's the insides of a state machine. From the outside of a state machine, you see this. You see in comes an array of inputs, and out pops one of the states of the machine. So this can be like determining, is this a valid integer, for instance, right? Each input is a character on the keyboard. If it's one of the numbers between 0 and 10, then you can keep it in one state. But if it's any of the other characters or between 0 and 9. If it's any of the characters between 0 and 9, you can keep it in one state, but then as soon as you see any other character, you just drop it to the other state, right? And that's a very simple function. It doesn't really need all this abstraction to be understood, but this abstraction, the point of the abstraction isn't that you use it to understand the example. The point of the example is that you see how the abstraction matches the example, right? And so the point then is to say, this is what we mean by a state machine. And so if you wanted to, and I'm not saying that when you recognize a state machine in your code that you should go do this, right? But what you can do is then take the language of the abstraction and make that the language of the code. But you don't, just because you can recognize an abstraction doesn't always mean you should write that into the code. That's really important. But if you were to write it into the code, the way I showed before on the video with the symbol sets about state machines is how I would think about it, right? You'd say, well, okay, I need a state finite set, and in that case of that particular system, the inputs were basically keyboard strings, lines of text, because I was using scanf to gather my inputs. And so I was implementing the transition function as my states, right? Each state wrote, if you give me an input, I will tell you what state to go to next, right? So the step function was broken up into cases, because that's what you do with a finite set. If this were an enum instead of symbol sets, you'd still have cases in your switches, right? It's a finite collection of differently acting things that are arbitrary. Now, if we wanted to, if we knew, for instance, that our states were just the numbers 0 to n, or 0 to n minus 1 or whatever, if those are the states, then you can do stuff with that knowledge that it's these integers, right? And you can build that into your model. But just thinking from this perspective of like abstract finite set, I plug in symbol sets, then the way I can implement this with a symbol set was that the step function can be a case-by-case thing, right? That's what symbol sets are good for, is case-by-case logic. But again, the abstraction doesn't have to be implemented in a way that looks like symbol sets, right? You could. The point is, these things occur all over the place, and redefining them as a specific piece of code isn't necessarily the point of recognizing it. But if you know the abstraction, then you can try to see if it's a useful tool, and that's what the symbol set state thing was exploring. But when I used that, I found that by itself a state machine wasn't really what I wanted. Let me show you a little bit though about how they map to lines of code so that you can see the way the metaphor is building what I'm trying to build out of the state machine. So the idea with the state machine to use them, the reason I was choosing to explore to use them is because they are often used in story engines and like any kind of game editor, game engine built for building interactive fiction type stuff generally goes that way. And I haven't always understood why, but I wanted to explore it. And so I wanted to, even if it wasn't going to be the model I thought I should run with in my own story engine experiments, I wanted to have better tools for building and testing the model, right? The model is, it's a state machine. Well, okay, defining that specifically like this, for instance, okay, I need to pick an initial state, which happens, in main, and a step function, which happens in all of the symbols that define state. Okay, well, I can write the code that will determine, the output state from an input. This seems reasonable, so I go and do that. Well, the next question is, what am I trying to I guess once I've got that ability to model it better, how can I tweak the model or understand the model and what it's trying to be and make it better, right? Make it work for more stuff. And the metaphor I clung onto is this idea that a state machine, and it's a little hard to explain how I see this without going all the way to Turing machines and then back. But the states in a state machine are like the lines of code in a C program. So let's look at the lines of code version first. Say I write some C code and it's like, x equals foo, y equals x plus bar, for I equals 0 to c I plus equals 1. You got something like this going on in your C code. Whatever, right? Stuff like this. So what does this look like to me in relation to the state machines? Well, when this turns into low-level code, it turns into machine code like this. So here's our, imagine this C code and how it translates to something like this in machine code, right? And underneath the hood, what you have is something like call foo, and then that gets stored into a register, and so then you do like move, maybe there's a return register, and you move that into R1. So into R1, remove from the return register, and then you got like a call bar, and then you have like add R into R1, and that doesn't work. So you have whatever. It gets annoying. It's like add R2 is R1. So there's the plus, and so this right here implements. This is x equals foo. This part here is y equals x plus bar. So the add happens, it goes into R2. So there's R2, there's R1, and then for loop, I don't even want to do this. What was I hoping that I would get this far and want to do the instructions for this part? The point is, whatever's going to happen here. So, the for loop. The point is, instructions underneath have this structure where you do one instruction, and by default you go to the next one, right? So you have an instruction pointer looking at an instruction, and it does an instruction and goes to the next one. Now, at the level of C semantics, or if you look at it in a debugger at text lines, what happens is it does both of these and then stops and says, okay, you're here now, right? When you're here now. You've done everything before. And so this line of code, similarly, it's like, okay, the instruction pointer maybe goes to the next line instead of the next instruction, but there's still this sense of you're in this instruction pointer, and then you do something that changes the state, and the instruction pointer moves to this one, right? So the thing that's not obvious here is that this is the same thing as the state transition. The states of a state machine are the lines of code, and the state transitions are like this extremely flexible branching mechanism, essentially, right? It's like from any line, that line could be rich enough to describe branching to a bunch of other lines, right? In low-level stuff, what we do is usually you always go to the next thing, right? You always just go to the next thing. Or once in a while, like, if I had done the for loop, there would be like an if here. If, well, I guess it would be like, first you'd set R3 to 1. And then you'd go, if R3, or you set it to 0, if R3 is, this should be I is less than C. So if R3 is less than R4, we'll pretend like R4 was set up here somewhere out of sight, just like how C is set out of sight up there. So if R3 is R4, go to done, right? And then, so that would be the part that skips the, you set I equals 0, you do a conditional check, and then you would do this thing. So you would do, this is, foo bar, this is the array I equals baz I, x, y, boom, and then you would do R increment R3 by 1 and go to loop, right? And then loop is actually this piece and done is this piece, right? So this is kind of how it would turn into instructions to do the loop a little more in detail while still skipping the annoying stuff. But we have this idea that now, okay, we have an example of jumping. So jumping is where an instruction just says, okay, I don't actually want to do the default, which is go to the next thing, instead go here, right? And that instruction doesn't do anything except implement this redirection. Whereas up here in the state machine, it's built in at every step. You could always, whatever you did inside the state machine, also pick a different state, right? You can always just pick a new state. So it's a little different feeling because of the fact that it branches in all possible directions. But there's another piece that's different. The if is also different because it's not deterministic. So this is a branch, not just a jump. It can go two different ways. It can do the default and go down, or it can do a go to done, right? And so these little building blocks in the instructions, a single branch that can go one of two ways and a jump, allow us to make this soup wherever otherwise everything's just always go to the next thing, right? It's always go to the next thing down in order. But these two little pieces allow you to build the shapes that resemble these high level ideas where branching is happening all the time in as many directions as you want, right? But besides that, right, this code down here, the instructions are also changing some state that is not included in the state set, right? So the finite set of lines, or like all the valid locations where the instruction pointer can be here, do not account for all of the states because of the machine, because the machine has organized a bunch of its state in this other section outside of this finite list of places where you can go to figure out what you do, right? These are the instruction pointers, but they're not the full set of states. So this is the difference between like like if you go into basic automaton theory stuff, and you look at a finite state machine or a discrete state machine. I can never quite nail down who prefers which namings for these things, but there's some kind of very formal version of a state machine where this is the state machine and this is the whole thing, that the whole set of states is just the finite set here and nothing else. And so when you specify your finite state machine, you literally have to specify the whole finite state. But then there's the practical thing, which is like this is this division into states which are telling you what action to take, and another set of states that receive those actions, right? There's the memory gets modified by the instruction, and the instruction pointer moves. And so your state becomes like this pair of instruction pointer state and memory state evolving together, but out of these little building blocks that cannot always just branch everywhere anytime, right? So that's the big difference between literally what happens in a state machine and at the instruction level. But if you just make the tweak of saying, well, my state machine has this, but when I defined this, I did not mean to say that this is a closed definition, but rather this is the rendering of a larger system down to just this much, right? That is, there may be implicit stuff going on that I didn't write, for instance, in this step function here, right? In fact, this is exactly what I mean. I'm saying, like, we're saying that you get to smuggle in for free the entire context of memory that the program has access to in addition to the finite states, right? So there's two different interpretations, and I'm not talking about the very strict automaton type definition where you like define the whole set of finite possible states in one go and consider that a closed system, because I'm talking about it as a programming interface. And so in any programming language where there's anything implicit, like a global namespace, anything you talk about is always actually an instance of participating in that sort of open-ended context, right? And so that's sort of the way in which it actually works with symbol sets and the way I intend for it to be thought about when I write it here, because that's how it actually lines up with the low-level thing, right? Okay, so that's all very fine and good, except that we've smuggled in something you cannot do quite yet with just state machines by saying it's going to be like code. But I want to also just mention, why would I want it to be like code? Well, this is in that spirit of trying to make C programming be able to do more of what you can do with scripting. At the shallow end, there's like, building quick models and being able to make them work quickly, and that's sort of what the symbol sets are helping with. But the other thing you can do one of the other things you can do that makes scripting so dynamic is that you can do coroutine type stuff, where even if you only have C and Lua and you didn't go and play with Lua's own coroutines, just having that makes it like a coroutine, because your C code can at any time, pause what it's doing, hand over to the Lua interpreter to do however much work it's going to take for that Lua interpreter to then yield back to you, right? And so you have the ability to move certain kinds of logic over into a different timeline from the one that's controlling when that time is scheduled. And the logic of that kind of division by itself is useful to have. And there are ways to get coroutines in C. I've done various flavors of this, but all coroutines always have this problem that unless you build deeper into your language that you want to support fixing this, that you cannot serialize a coroutine very easily, right? Usually, like in C, for instance, a coroutine means you have a thread, or you have at least set up a stack and you can context switch or something like that. You have a whole separate stack. Somehow you get the context for that stack separated out cleanly and the ability to hand off back and forth one way or another set up. And then once you can do that, you can run one coroutine and then switch to the other one and back like you're supposed to be able to. But if you start to encode fairly complex states, like partially completed things, that need to continue to be completed, and you want to have the ability to sort of save that and then come back to it later. Say, oh, this is, we're going to pause this session. Well, what happens when a session can contain incomplete coroutines? You just have to figure out how to abort them all and clean it up and say you're going to lose these partially completed interactions or whatever. And for a lot of use cases, that can be kept at the level you want it at, but it's always bothered me that you couldn't do any of the things you would do if you could just serialize the stack. So as I'm looking at this relationship and I'm trying to think, what could I do? I know story engines are based on state machines a lot of the time, or state machines plus this, they also have the variables, right? They're not using formal discrete state machines. Story engines are using state machines plus variables. So, it's that. But why not go the extra step further and say, well, when I'm writing code and I want to be able to have this sort of scripting feeling of like, I can pause this timeline, find out logically what happens in the simulated timeline, and then sort of gather that information and process it over here when it's ready, without having to just figure out how you're going to unencode and decode and re-encode the machinery of the simulation every time, right? You want that just clean coroutine separation of some other timelines logic happening somewhere else. Well, though you can't do that with a basic state machine, even with variables, is basically the point, right? State machines just don't have that, because the key is that you have a stack. The key is that you can go a little farther, and this is something you do learn in discrete, the formal automaton theory is like the ordering of like discrete state machines can't do things that stacks can do. And the confusing thing there, and the reason I don't necessarily think that going into the formal old school stuff is worth it, is because for the stack machines to be considered worth it, the one they really like is like the non-deterministic pushdown automaton in particular. But again, that just gets farther and farther away from how things work. That's even more of this like arbitrarily open-ended branching logic that doesn't really map to how low-level thinking works, because everything's built out of this very small amount of, there's a default flow, and then there's a couple of ways to make exceptions, and out of those exceptions you have to build the shapes of the more interesting flows that the high-level models just take for granted. And when you take those realities into consideration, you get different kinds of models that are better for literal, like actual code maintenance kinds of reasons, right? It's just because it's real. It matches. It doesn't take you too far away from the low-level performance shape, I guess. So, okay. So, because we want to be able to support calls, what we need to do is look at how I fibbed about calls here, right? So the difference between a state machine and a stack machine is the difference between an instruction set that does not have a call instruction and one that does. If you just took what I said before for granted as literal, you would think that when you use a call instruction, you go to the next thing. But actually what happens first, before you go to the next thing, is you jump to foo and you do everything there until it says return. And what happens is that the shape of the stack, so this is where we get to 2b, and I'm doing 2b before 2a because that's how things turned out. So 2 is stack machines, and so this is lines of code metaphor. So what happens when you actually do have a stack, we need to set up a little stack graphic here, is that instead of having a state, right, you can imagine that a state machine is like this thing where its state right? It's just, there you go. It's just a single, it's just a state, right? That's the point. It just has a state. But a stack machine is gonna look like this. Right, with this being called the top. And the top of the state machine, or the stack machine, is going to give us a state, right? But at rest, it doesn't just have a state anymore. So the thing that happens, we build a new definition. Let's build a new definition up now. We still have a set of states. We still have some set of inputs we're going to process. And we're still going to process that some of the time by doing what we did before. So let's start there, right? We start with, here was our old way of doing a step. Now the problem with this was that it didn't include the possibility that when we do a step, we are also going to be allowed to change the stack. So just like we did before with state machines, it's not like we're going to think about this in terms of literally what you can do out of instructions. And so we're going to say, make a sort of a closure where anything at all, like large bundles of instructions could build, can happen in a single state. Just like how in a single line of code, multiple instructions can happen, in a single state of the state machines built out of symbol sets, multiple lines of code happen. And so it's a grouping of all the things that happen together and a label for that particular bundle of state transition information, right? So a stack machine looks like this. Where was I? In step. Okay, so the change is that in addition to picking a new state, sometimes we're going to want to pop. So we have, it's going to start getting more complicated, right? There's pop or pick a state. Or, and then here's the thing. If we say this is like, this is like a sum type now. So we have, there's the pop case where there's no information. There's next, which is just like the old version of where you always had to pick a next state. That's what next is. If you are in the next case, then that just means you want to change the top of the stack. And so the idea here is that each layer in this stack can just be a state machine, except that if it wants to, it can push or pop, right? And so you could always just turn your stack machine into a state machine by programming a state machine on it and not ever pushing or popping from that state machine. But we've equipped the machine with a new ability which allows the things we write inside it to attach to that abstraction, and so they can mean different things and sort of compose differently to each other. Okay, and so the other thing you can do is a push, right? Now, if you just said a push was a state, then what you would get is like if you could call foo. But what happens when you call foo and then it's done and it pops, and what it finds is it finds itself right back here, right, on the call foo. That's what it would be like if this was what you did, right? You would push a state. The state underneath would remain where it was before you did the work. But this is supposed to be telling us what we do next. And when we push, we're really just and also when we call a function, we don't necessarily think about it because the trick of function calls and procedural syntax is this default flow forward, right? Instructions and in procedural code have this default flow to next built in. And so a function call looks like a jump to one place, but it's actually simultaneously a jump to two different places at two different points in time. Right away, it jumps you to foo. But when you're done with foo, it default forward flows, right? It doesn't, the next state was automatically picked for you by call. And so in our state machine, we don't want to be in a situation where every time we push a new state, it's always go back. Now, that's not necessarily the case that you never want this, right? Right here, we have Baz getting called in a loop. So in a sense, this one line should happen multiple times. That makes sense that sometimes the logic is you push and then you come back to right where you were and do the same push again. or do the same instruction again at least. When you pop that. But that's not the generic case. The generic case is that you push, and also when that pops, you don't want to repeat what you did to push. You want to flow forward, but like how instructions that have flow forward as a default, you don't have to say where they go. But then when you specify it as a state machine, you do have to specify where it goes. Same here, when you push, you have to specify not just what you're calling, right? But also, so this is why it's next and push. Also, you have to specify what would be next at this level, because state machines don't have a default next the way the code does, right? So again, the idea here is next is implicit in procedural code. In state machines, it's explicit, and so calls have an immediate jump and an implicit go to next. Stack machines have an explicit next push. That's the idea. Hopefully that about does it. Let me clean up my definition if I didn't. So yeah, that is the main definition. So it's basically build from state machine, change the step function to look like this, right? And so that's it. You just take the original and you do this. The init state becomes the initial thing on top of the stack with nothing underneath it. The step gets upgraded so that instead of always returning a state, it can also return pop, or it can return a next state and a push state. And then you still have the same. How you want to interpret this outside of the machine part is up to you. Again, this is supposed to be very open-ended, so this is a little bit of a fib. Like, you could easily be like, no, it's actually not about the state. I actually have an output type, and you calculate the output type from the state or from the stack or whatever. Like, you know what I mean? Like, it's open-ended model building. This is not closed model building philosophy. It's open-ended, so my state machines have all of this, or my stack machines have all of this stuff we've talked about. Plus, there are things like in my RPG engine where I am using this stuff. The stack machines also have stuff attached to the layers of the stack, like, is this a layer of the stack where there is an active field with characters on either side of the field, and what kind of locations are there in that field, right? What's the topology, is what I call it, of the field at this level of the stack, if applicable. Or I can time memory management to these layers of the stack, and I can have multiple of these stacks and treat them like coroutines and schedule them from the C code or from each other if I want, right? Like, I haven't gone into how you would do the coroutine part exactly, but it's basically you keep multiple copies of the stack machine around and you run them either from a central scheduler or from each other or something, right? Yeah. So anyways, that is a quick spiel on stack machines and how I think about them. I think the big takeaways that I would like for people to, I guess I didn't end up using this at all. I used a totally different kind of notation in the end. The thing I was going to go for was possibly to say that, like, this and this can just be defined as a couple of integers. And it's true that if you want to, you can boil these down to index systems, where you just have indexes for states and inputs and you build this mapping. Or you can attach procedural open-ended context to it the way I was intending, and that's why I wrote it this way. And so I guess I don't know why I was just like looking around for what syntax or notation I wanted to use to convey it, I guess. But yeah, that mostly sums it up. Hope this was useful.